Thank you for your presentation. Thank you for inviting me. In fact, well, I am so happy to be here. And I will tell a story today, not only about science, but also how through science, we were able to protect an unknown place that has a lot of potential in biotechnology. So in that way, I will invite you to travel. Since I was traveling 24 hours to come here, I will invite you to travel to the beginning, or again, it's not my presentation, sorry. Not. Okay, it's not. Well, here we are in the Pune systems. So, as I was telling, I will invite you to travel, but to travel for let's see. Perhaps I am going. Okay, okay. So we are going to travel on time. We are going to the beginning of the universe, a long time ago, 13,000 millions of years ago, where the universe came. And the idea I would like you to have from here is that all the elements of the periodic table come from the beginning of the universe, from the stars, from the supernovas, and that's the way we have all the elements that are in the universe. All these elements are inorganic elements, and the most who recycle better these inorganic elements to organic elements are microbes. In fact, microbes were dominant during the complete history of the life on Earth. They were dominant on Earth during more than 2.4 million of years ago. Okay, in fact, I introduce you how it would look like the early Earth, such a long time ago, when it was the Precambrian. Okay, the Archean. In that moment, there were no oxygen in the atmosphere. The continents were forming, so there was a lot of volcanic activity. There was no ozone layer, so there was a lot of UV radiation, even UVC radiation. The water, this primitive soup, was very alkaline, very high salinity, and full of content of arsenic and sulfur. In that moment, I can show you these little rocks you can see here are called stromatolites. They are the oldest fossils we have registered. They are made of bacteria and cyanobacteria that cut the carbon dioxide from the atmosphere and transform it in calcium carbonate. And in that process, they made photosynthesis and liberate during millions of years oxygen to the water, to the sea, to the ocean, and then to the atmosphere, and create the ozone layer. So I introduce you the stromatolites, who through the history, the last 500 million years, they were in charge of reconstruct the atmosphere after the 5 big extinctions there were on the planet. Those extinctions were because there was a huge amount of carbon dioxide in the atmosphere. It can be because of explosion of a big volcano or the impact of a meteorite, whatever. They were in charge of reconstruct the planet each time. The last massive extinction was the dinosaurs one, who prepare the planet for the dominance of mammals, who are pushing up the planet to the next massive extinction, liberating such a big amount of carbon dioxide to the atmosphere. So I introduced them, that those are the stromatolites, these living rocks, as I told. I named them living rocks, is contradictory, but it's true. Geologists don't look like that too much, but they are living because they are made of bacteria and calcium carbonate. They are always growing, and you can find them in some places on the Earth. For example, in Australia, in Shark Bay, here in Bahamas, in United States. They are all placed near the sea. But let's keep on traveling. Let's go Let's go to South America, to the highest and driest desert on Earth. It is named Puna in Argentina, Altiplano in Chile, or Altiplano in Chile, or Cordillera de Atacama or Altiplano in Bolivia, or Cordillera de Atacama. This is a closed basin surrounded by active volcanoes who are still influencing the geochemical and the chemical situation of all the brines and lakes there. We are placed at more than 4,000 meters over the sea level until 6,000 meters over the sea level. This is the place. This place presents a lot of situations that are similar to the early Earth, because they are surrounded by active volcanoes. Remember, the early Earth was still forming and there was a lot of volcanic activity. They are buried because they have high altitude. They are placed over 4,000 meters over the sea level. So there are a lot of UV radiation. Because of the high altitude, there are low oxygen pressure. And it's more important, the lakes there, the water there presents a lot of arsenic, sulfur, high alkalinity, 5 to 8 times the salinity of the ocean. So it is very similar to the primitive soup where the life began. And what we have found during 2009, I was studying the UV radiation systems in these lakes, how bacteria cope with radiation in this environment, and by serendipity, I found these stromatolites in the lakes near active volcanoes in La Puna. It was such an impact of this new, that it was a new nature, and we realized it's something that happened once, I think, in a microbiologist's life. And in that moment, I knew nothing about the stromatolites. I am microbiologist, but I am not geologist, and I had to learn about stromatolites. And we had a lot of tasks to study these stromatolites. One of the biggest tasks we have is that these places are very remote. To get there, you had to drive a 4x4 wheel truck during more than 2 days. We are isolated out of any kind of internet or any kind of contact with civilization. In addition, this area is becoming the triangle of lithium, because it has more than 90% of lithium reserves in the world. And as you know, in your telephone, you can have lithium batteries are made of, the batteries of your phones are made by lithium. And now many cars we have lithium batteries. So there is a lot of impact and prospection in lithium, and in fact, they are destroying this environment. In addition, this environment, this land, this salt brines belongs to ancient original communities that have been there before thousands of years and has suffered years, centuries of injustice since the Spanish came to South America. And at last but not least, we were a small team made mainly by women. So I realized in that moment that we had to save these living rocks. The first thing we did was prospect to know if that microbialites we have found, stromatolites, let's name that like that, we have found in Socompa were a unique situation, or it was in all the Andeans. So we started to look for this kind of rocks that has been studied as rocks or never studied. And we went all through the Andeans in, in Bolivia, Chile, and Argentina. So we were more than 15 years traveling, going to this place, in literally being in a 4x4 wheel truck half of the year, going to places that no one has been before, inside the volcanoes at 6,000, almost 7,000 meters over the sea level, to salt brines. And many of the places I will introduce you today where we were the first to arrive to these places. Let me introduce our system. As you can see, they are all different. All of them are rocks, can be confused with rocks. And in Argentina, in Chile, and in Bolivia, we produced a lot of science, a lot of publication about that. All that this science is published if someone is interested. And what we have found also is that they are made of gypsum. They are made mainly by organic materia, by calcium carbonate, or even though there are some of them that are fossilized in the center and still alive around. So they are living fossils. They are formed by bacteria, by cyanobacteria, by diatoms, and of course by minerals. And we have made different groups, and we have studied them from the protist point of view, studying bacteria, studying prokaryotic diversity, viridome, microbiology, molecular biology, geology, and metagenomic and metatranscriptomic. If someone is especially interested, we can talk later. I will only give some examples of all that science that we have been doing during the last 15 years. So the first thing we have found is that concerning UV radiation, there was a spread of mechanisms for cope with UV radiation was directed with the high altitude. More high altitude where the system, more UV radiation, more photo receptors we had. Even we had new ones. In fact, we can, yes, as you have seen, they are placed on layers, and on those layers there was a different spread of the biodiversity, and that biodiversity present all the mechanisms of the geochemical cycles that cope with the high UV radiation, with the low oxygen pressure, and with the high salinity content. But in fact, what we have found is that all the geochemical cycles that we find in a planet, that we can find in the ocean, are placed in these 10 centimeters of microbial mass. What we have also found is that there are a mobilome that these genes involved in surviving to these extreme conditions are spread in all the community by plasmids. And these plasmids, like for example, UV radiation genes, arsenic resistant genes, all are spread in the community by plasmid, and even though even they are pristine, but they are still spreading antibiotic resistance. So let's talk about how they take the carbon. So I want to introduce a new concept we had think about for these places, because these places are considered driest. They are considered sterile. In fact, when the mineral company comes, they say it is sterile, no problem with biodiversity. Well, yes, there is a problem with biodiversity, because we have found that under the salt in the brines, there is still Extremophiles, and that those Extremophiles are made of cyanobacteria and other anoxic bacteria that are respiring and are producing oxygen just like a forest. So we name them biosalars or salar forest or brine forest. Let me show you one of the picture. I won't talk too much about that. But for example, this is when we measure the oxygen production or photosynthesis during night and day in 2 millimeters scale in this sterile brine, we found that there is in the beginning of the morning, there is at 9 a.m., there is a peak of photosynthesis that is more active during the noon. And it is deeper because it goes behind the salt to protect of UV radiation. Remember, we are placed at 3.9 thousand meters over the sea level. We describe all this metagenomic with the metagenomic analysis that not only Calvin cycle, the typical photosynthetic way of make glucose, but also very ancient way of produce carbon cycling. We also found we also found that they are very active even though without oxygen. And talking about oxygen, I want to invite you to travel to Laguna Diamante. Laguna Diamante is one of my favorites. It is placed inside a big volcano, a big caldera that is a Volcan Galan. Volcan Galan is placed over 6,000 over the sea level. Inside there is a big caldera of 40 kilometers where there is a lake that is called Laguna Diamante that is placed at 4,500 meters over the sea level. pH is almost 9 and can get to 10. We have 8 times the salinity of the sea there, and is the place where more arsenic in the water, naturally in the water, was found. For example, Mono Lake, California has 19 milligrams per liter of arsenic. Here we have 300 milligrams per liter of arsenic. In that place, Raskovan, one of our PhD student, found that there are rocks. These rocks might be stromatolites, but they are surrounded by this red biofilm that is made by Lucida. Lucida is a calcium carbonate. It's hard to say it in English for me. Un carbonato de calcio pentahidratado. Oh, sorry. It's a mineral that is precipitates only with high pH. It can be found in Mono Lake, California. It can be found in Magadi Lake in Africa, and it can be found in Laguna Diamante. But this mineral is always no color, colorless. And in this case, it presents this rubber color. Why? Because it is dominated by archaeas. In fact, 94% belongs to archaea, and among them, Allorurum is dominant. So we study the metagenome of this environment, and we found that it is dominant by arsenic respiration genes, mainly ARA and IOAV arsenic. That is a gene that is needed for respiration of arsenic without oxygen. I don't like this. Okay, where we cut the back, the Allorurum, we sequence it, and when we analyze its genome, we found that it is full of oris that belongs to bacteria. So these are an archaea that has a lot. You can see here. When it drops, this line drops, it belongs to, because the height is C, it belongs to bacteria. It doesn't belongs to archaea. And all these ori are next to arsenic resistance genes. So here we have an archaea, but here we have a chimera of different genes that were adapted and were interchanged to cope with these extreme conditions. Well, sorry, when we compare this archaea with all the allorubrum sequence in the genomic data, we found that it is very, very far away of the other genomes. But when we compare the IOA gene with all the allorubrum in the database, we found that only the allorubrum that is isolated from the Andean lakes has this gene, IOA, for respiring arsenic. So if you want to live in the Andes, you have to have these genes. And when we compare all these genes among them, these are the allorubrum genes. This is a allorubrum who has from Andeans, who has these IOA genes, okay? Comparing IOA genes from other phylogenetic bacteria, we found that all the allorubrum who has IO genes, these genes is very conserved, is very old. It belongs to when you have the phylogenetic tree of life, it belongs to a bacteria that exists before prokaryotic and archaea were divided. So this is this very old system, very primitive system, was also found in Piavara fossil stromatolites that has 2.7 billion years ago, where arsenic was found next to organic matter production. It was found in a fossil stromatolite, very old one. But when we studied our system, we have exactly the same situation. Archaeal dominance of the systems, and we found also arsenic attached to organic matter, just like those Piavara systems 2.7 billion of years ago. So here in the Andes, we have the same situation and the same system for respiring arsenic and producing organic matter through arsenic without oxygen. In fact, in our paper last year, 2 years ago, we were able to demonstrate that this is one of the unique places on Earth that is in presence of oxygen. This is in Atacama, and it produced not oxygen at all during 9 nights and days. During summer and winter, we were there 5 years, during 5 years, to do exactly the same measure, and we never found a peak of oxygen. So this system is working such as this primitive situation that was on Earth. In that way, we propose this early Earth photosynthetic system that use arsenic and sulfur to precipitate calcium carbonate and produce organic matter. So what we have found in Andes was Luca. Luca is the last unique common ancestor. We found a system that is supposed to be in this original cell that gives life to the other forms of life as archaea, bacteria, eukaryota, etc. So we had to save Luca. How you save a bacteria? It could be easy to save a whale, for example, or a bear. It's more, everybody knows that bears are on extinction and everybody takes care of bear or whales, but how to save a bacteria? Let me show this way we have been taking care of the systems is first we introduce these systems to the all native population in the Andeans, and they produce their own publications. I am so proud of them. That is the way they were able to explain that there were living rocks there, that there were stromatolites and extremophiles there. We talked with the mineral companies, and we were, in some cases, not in all the cases, but in some cases in Chile and in Argentina, to produce, first of all, knowledge to monitor, to follow the health of the system, first of all, and then we were able to protect some specific areas. In fact, we saved some specific areas for a perforation from lithium companies. This is some of the places that were saved by now, and we produce also knowledge for everybody to understand how to take care of the system. It is very well used, very used in Chilean, and we were able to get the declared protected area in Laguna Socompa, the first place, and also Santuario de la Naturaleza in Atacama, Chile. So the next step was to make this system to produce money. That's the best way to say them. So we became, because conservation is not only, it's also about economy, how to make this ecosystem more valuable and also demonstrate that they must be preserved. What I did in the first place was to transform myself from a Humboldtian biologist who is searching in nature. I became a biotechnologist, and I will very shortly tell you that story that began 2 years ago. One of the questions I made when I was in the Puna was how plants can grow near the brines at 4,000 meters over the sea levels with no water, with such a lot of elements, arsenic, sulfur, and with oligotrophic conditions. What we did was to study the resources of that plants, to isolate these microbes, to take them to the greenhouse and then to do field trials. And what we have found is that they were able to solubilize phosphate, to fix nitrogen, to produce auxins, polyamines, enzymes, and different enzymes, and to produce siderophores and form biofilms, and protection against fungi, not only in normal condition, but also in high salinity and driest condition. What is more extremist environments, better they work. So we took these bacteria to the soil, to the crops, and we found that they were able to induce the crops to grow not only with high salinity or degraded soils, but also they improve the crops yields in fertile soils. This is some trials made on degraded soils where the control didn't grow at all. And in fertile soils, you know, in Pampas, we have the best or one of the most fertile soils on the earth. You can see the control in soybeans versus our product, and it also happened in corn. Here is we did 3 field trials to get the approval of our product, and we found that we have increased yields comparing the commercial product, and what is more important, it always works, because biological products, the problem of biological products is that sometimes they work and sometimes they don't, sorry. But we found that our extremophiles are able to work in very extreme conditions, and they always work. our biofertilizers are these recycles of the first recycles of stardust. So they work at 40 degrees, they work at 50 degrees. That is one of the cases in the north of Argentina. They worked in these field trials this year that was the driest field trial ever in Argentina, and they still worked. And they also were able to biocontrol pathogen as many of the fungi that are very, very problematic in soya in crops in Argentina. So to tell very briefly how I became a biotechnologist, well, since last year, 2 years ago, when we started with produce from a small tube of 10 milliliters, we went to 4,300 liters. We produce inoculant for 600 tons, and we work for more than 40 companies. Last year was a great year because we get our seed round to have more money to do more field trials. We started our field trials here in the United States, in different states, and in Brazil. Brazil, Argentina, and United States are the main producers of soya in the world. And we produce 19,000 liters, and we get our regulatory approval in Argentina, but with Nagoya process. That was the first Nagoya process that was taken in Argentina for this kind of development. In portfolio, we're expanding to dry beans, to corn, to wheat. We have another bacteria that works very well by fixing nitrogen, and it works better than those genetic modified bacteria. So in parallel, we are creating our Noé Ark of Extremophiles microorganisms for biotechnology. We go to this remote place in the Andeans. We do this prospection, take it to the lab, license all this biotechnology directly. It was a hard to license, but we just are in that process, and we are able to license all the biodiversity we get from the Andes, and then release its potential for multiple uses, not only for our company, our small startup company, but also to license to the third partners. So this is can be strategic partners. So all is done with Nagoya protocols, which means that there is an equal distribution of the resource. These people that lives 12 hours 4x4-wheel truck from a hospital, that they live without light. Now they are receiving part of our company economical benefits. So I introduced the part of the team that was going with us to produce all this knowledge during all this year, and now my partners that are scientists, Elisa and Carolina, were from the team that that did science with me and came to the startup, and Franco Martinez Levy, who is our CEO and is in business. we need to know about business. And for finishing, I want to let this draw made by Valentina, who is a girl that goes to school in this remote place, and she learned very well what stromatolites are. So thank you very much.
Here in St. Louis. I loved your talk. I think we should all stand and clap. So I'm going to stand and clap. That was
okay.
Spectacular.
Thank you. Thank you. Oh, thank you so much.
So, no, seriously, two questions. One question. I love the fact that you're obviously working with local schools, it looks like. And I was just wondering, it seems like you've been there for more than a decade. Have any of those children then gone off to universities in Argentina or other countries and now are becoming scientists? Is that sort of feeding the pipeline of scientific knowledge? Can you comment on that at all?
Yes, well, that is my concern, is that this child, in fact, I have been working since 10 years ago there. For example, in Atacama in Chile, there are, we call Ayus. Ayus are very ancestral communities, and they were getting lost because all the people from there were to work in the companies. So with this putting value of the systems, tourists came, and we prepared this child that was teenagers in speaking in English and explain about the place, the origin of life, that is the Mars and look for life that are very similar and so on. And now those Ayus are getting saved because the young people is staying there, telling to tourists about the origin of life. And these Ayus will be preserved because those kids will stay in those Ayus. In the case of Argentina, now that we became a small company, we have money, and though we are going to by responsabilidad empresarial, company responsibility, I think it is. All this business name is still not very familiar to me, sorry. We will support those kids to go to the university and become biologists and geologists, because it's very important that these baselines of the mineral companies, that they work in the mineral company by being experts, not only by, washing the clothes. Okay, do you understand what I mean? Okay. So we are so involved on that, but still we are a small company. They received part of the well, it was the first field trial. First campaign was this year, so they will receive the money and can grow with this education. Anything else?
Sorry, I missed most of the talk. Had some work to do. So I noticed that you mentioned the natural fixation, right? So you identified some natural fixed bacteria from extremous environment, right?
Nitrogen fixation.
Yeah.
Okay.
Yeah. Is that free living natural fixed bacteria?
Yes, we are. I cannot talk too much about that because we're still working on the IP. But we found that it is just the same of benchmark, which was GMO microorganisms.
Yeah, I'd like to know what's the big difference in terms of nitrogenous structure, or the contain molybdenum metals there compared normal nitrogenous,
yes,
or oxygen tolerance or not.
Yes, sorry, yeah. I am not allowed to talk because we are on the IP process. Sorry.
Thank you.
And
she wants. Sorry.
Go ahead.
So can I just ask you one question? I'm interested in that Haloruro bacteria.
Halorubrum.
Yeah, that has this arsenic metabolism. So have you ever thought about using it for putting in plants for remediation of soil that are contaminated with arsenic?
Yes, that is one of our portfolio application. The problem is that during all these 15 years I have been working there was plenty ideas for biotechnological application, but the good one was this idea that was one of many that could go through the bureaucracy, the Nagoya Protocol, all the ways that science from the paper goes to the biotechnology application. And in Argentina, it's more difficult because there is not too much experience about that. So now we have the company, now we have the way, all these ideas we are hoping to take to the biotechnology and to produce solutions